Good evening. Today we are going to discuss a actual DOE project which I have conducted in the year 2007, and this project was very good, and the saving of time was around 40%, and I'm so happy to share with you the this project where I worked along with the production team to reduce the cycle time of turning in a CNC machine. So, what is the objective of the project? It was optimization of turning operation of pins to reduce time of turning, thereby improving the productivity of CNC lathe machine. Actually, we were manufacturing these high carbon, high chromium pins for our plant, and it was done in a CNC machine. However, this turning operation was taking a long time. So it was decided to take a DOE, Six Sigma DOE project to see that this time is reduced so that we are able to meet the requirements, daily requirements of pins for that particular operation. Little later on, I will explain you what are those pins. So if you see this process flow, this is high chromium, high carbon, round bars will come, that will be cut into pieces, and first rough machining will be there, and the process requirement will be that it will be less than 1.6 micron. The roughness will be less than 1.6 micron, and next it will be hardened, and then again it will be machined. And here the surface finish requirement is 0.6%, 0.6 micron, and then this will be going for the use up to the machine. So this response was a variable response. What was the response? The roughness of the product. And so for the rough finish, it was 1.6 micron, and for the smooth finish, it was 0.6 micron. And these are the pins, you see. These are the finished one. This is a so these round pins, they call it, or round bars, used to be fitted in this mold, steel molds, and this bar will go inside this mold so that the bricks which are being made will have a hole. This was probably a 18 checker High Alumina bricks used in the refractory plant, being made in the refractory plant. You see this assembly here. So what is the process? What is the process stage? It was the turning operation. Process stages where optimization to be done is turning operation. There were two turnings. One was the rough turning, and there was fine turning. And whatever the earlier value, current value was, average the rough machining used to take 35 minutes, and the fine machining used to take 55 minutes. So a project planning was conducted, and this week-wise monitoring was there. And this was, you see, from 15/10/2007, the project was completed in, it was finally completed on 26/11/2007. So these are the different jobs to be conducted. It is all written here. And there it has got 4 phases: define, measure, analyze, improve, and control. This is the this this is a DMAG phase. DMAG means this is the any Six Sigma project that is taken up is covered, is called DMAG, because D stands for define what is the problem, define the problem, then what is the present performance of the particular process or product, and find out the make an analysis of the causes, and then you make the improvement. You incorporate the improvement based on the your analysis, and then of course then you will monitor on the daily basis, so that this objective of the product, I mean the manufacturing of the product, is as per the your desired specification. So this was done with the problem was defined, and we found this problem was process parameter optimization is the this is the process parameter optimization was the job of the objective of the project. Now, process optimization for what is the objective? Process optimization for existing process, that is turning operation of pins, to identify the contributing factors and setting conditions. So, in what type of this DOE would be doing? We did. It was a full factorial. Full factorial means both the variables, whatever the factors were defined, the complete set of experiment would be done. There are fractional factorial, half factorial, etc. But it was full factorial. That means whatever factors and whatever levels were chosen, they were all completed. So there were two variables which was identified. One was the job speed, it is the speed of the chuck of the lathe. The other one the feed, the depth of cut per revolution. So these two were brainstormed. These two are the two parameters. And now we do a simple checking procedure how these two are the contributing factor. There are many ways of doing it. Actually, there you have to do some pre-screen, that is called screening experiment, and those screening experiments are like this. For raw machining, what do we do? You take 3 readings in the minor setting. Minor settings means we have taken the job, the RPM as 300 at the lower setting and 400 at the higher setting, this one. And this feed in millimeter per revolution was taken from 0.4 earlier to 0.2 now. Okay, and then we conducted for each setting, which this is called negative setting because the values are lower values. So there we took 3 readings, and in the higher condition we took 2 readings. Then there is you took the median. Median means which is in between, in the third, in a ascending order, which is the middle one. So it was 4 here in this case, first case. Here it was 1, the second case, and this range is the difference between the two medians. In this case, 4 minus 1 is equal to 3. And what is the range? Range is equal to the maximum minus maximum minus the minimum is the range. So here it is 5 minus 3.8 is equal to 1.2. Here 1.2 minus 1 is equal to 0.2. So the range is in this case 1.2, here is 0.2, and in the other one the median was 4 and 1. So we took a ratio. So difference between two median is 3. So the ratio d by d. What is d by d? D by d is d is the average of two ranges. What are the two ranges? One ranges were 4, one range was 1.2, and another range is 1.2. So 1.2 plus 0.2 is equal to 1.4 divided by 2 is equal to 0.7. So this is the smaller d, and this bigger d is the difference between two medians. So then we took the ratio 3 by 0.7, and the ratio was coming 4.2. So if the ratio of d by d, that is what is d? D is the difference of two medians, and smaller d is difference of two ranges, is equal to, in this case, 4.2. If it is greater than 3, that means that whatever variables we have taken, we have identified are the correct ones. And we did this DOE experiment. These details, as we are proceeding in the video series, in this DOE later classes will explain. But this is a Pareto chart which tells that the value of B. What is B? B is depth of cut. B of feed. This has got a bigger contribution in the time, and similarly, in the roughness. And similarly, this ARPM is the RPM of the chuck, is having a lower contribution in the roughness of the, because the final variable is roughness. And we did this contribution of each. It is a reflection of the previous one, where this is the B, this is the B A RPM we have seen earlier here. This is the RPM we have seen. So this has got lower contribution. You can see the slope is low, so this is having lower contribution, and this is having higher contribution. And these two variables are, these two are not having, since they are parallel, they are having no interaction. They are independent in the sense that one doesn't, one setting doesn't affect the other setting. Means the feed setting doesn't affect the setting or the contribution due to the depth. So depth and speed are not having interaction. And finally, from the DOE, by using Minitab, we get a regression equation, which is like this. This is 1.2 minus 0.006 into ARPM, means RPM, plus 11 into B feed, depth of feed, plus 2.2 4 to the power E minus 0.22204 into E to the minus 17 into A RPM into B RPM. So it is a very negligible. So that you have seen that this negligible, that A and B has got no here. You see the A and B has got no. It is almost zero. A very small one. So this only then now and setting up 500 RPM, and we did a optimization test, which will be again uh, uh, studying in the later videos. Actually, this whole project I am explaining you to show that what is the drastic improvement we can use in DOE. This is for our motivation purpose. That DOE is a very powerful tool and it leads to very large improvements. So from 300, we took the minimum and we did the test in 400, and we now you are taking the optimum one when the time is minimum. And you see the existing case, the timing was 35 minutes, and you see in the present in the newer setting, that is 500 RPM and 0.25 depth, it is only having 10 minutes. So much of reduction. So 35 minus 10 is 25. 25 minutes of reduction in the level of 35. So it is almost 70%. 70% reduction is there. Similarly, for the smooth finish, we have done this test, and two major variables again: job speed, that is the chuck speed, RPM 200 and 300. We did the test, and feet millimeter over per revolution was 0.15 and 0.12. And again, same thing we did. We took in the negative settings, we took 3 readings, and in the positive setting, we took 3 readings, and we found out the median is 0.8 here, and here 0.04. In the second case, range is 0, because all are the same. Range is 0, 0.8 minus 0.8, 0, and here the range is 0.6 minus 0.4 is equal to 0.2, which will range is equal to highest value minus the minimum value. Similarly, now D is the difference between two medians. Difference between two median is 0.4, and difference between two ranges is this is the average of two ranges, that is 0 plus 0.2 divided by 2 equal to 0.1, and you made the D by D is equal to 4. That means it is again greater than 0, greater than 3. That means that these both has got contribution. Now again we saw here in this case the RPM has got a bigger contribution in this case, and the feed has got a lower contribution. Means it impacts the RPM impacts more. That's why we have kept 500 more than the pressure sheeting, and here we have reduced the depth of cut. And again we got a equation like this, y equal to something like this, 2.4 in terms of A and B. Again here the RPM and feed was having some interactions. So our objective is to save timing, keeping the smoothness under the boundary condition of 0.6. So other condition was to keep the tool where same. So we decided a new setting of 300 RPM and 0.1 for this is for the EA one, for the second one, for the smooth one. And current old setting was 200 and 0.1. So from 200 we took to 300 RPM, and from 0.1 millimeter cut we took to 0.12 cut. And timing was earlier 55 minutes. The new timing was 45 minutes. So again there is saving of 10 minutes. So totally the saving of earlier it was 90 minutes. Now the saving is the total new cycle time is 55 minutes. So 35, that is a difference of 35 minutes over 90 minutes. So it was around 40%. So 90 minus 55 divided by The original 190 into 100 is equal to 38.8. So the improvement was 40%. This is a huge improvement for the cycle time. Now, anybody who is having this turning operation can always do it. And since lot of plants, they are having this type of turning operation. And if one does this analysis of depth cut and RPM, it will have a huge benefit. I just showed this example as a motivation of using DOE, this DOE technique. And DOE technique is actually the final implementation part of the Six Sigma. And the normally, if a right problem has been identified, you will have a great saving. So this is all. And if you have some points, I request you to kindly comment it, write in the comment box, and I will definitely reply. And based on your feedback, I will also give some, make some. My future videos will be as per this. Actually, this one is based on the opinion or the comment on one of my viewers, and I'm happy that I could. I had committed this weekend. Of course, I couldn't do it yesterday, so today I have done. So, friends, if I am going to put now the videos on the DOE, which is very powerful technique, and those who are working in the area of production, manufacturing, process plant, they will have a great powerful tool at their disposal. So please watch out for my videos, and if you have not subscribed, kindly subscribe it and hit the bell icon. And if you like it, please click the like button. So thank you, and looking forward to sharing more videos on this great technique that is called design of experiment. Thank you.